First of all, thank you very much for the invitation. It's a big pleasure to be in such a beautiful place. So I'm going to talk about band matrices. And so let me start with the classical questions that arise in this field. So there is two classical questions that closely related to each other. So I have to speak loudly. OK, so the first question is a classical question, is about the typical length scale of the eigenvector of these matrices. So we consider the eigenvector, and if more or less all the elements are of the same size, we call that it's delocalized. And if we have some elements that are bigger than other, we have that it's localized. So the localized eigenvector corresponds to the lack of transport, so to insulators. And if you speak about the statistics, it corresponds to Poisson spectral statistics. The delocalized vector is opposite. They corresponds to conductors, so to the diffusion, and to GOE or GOE statistics. So if you speak about random matrix series, the more classical question is so-called local regime of the random matrix series and universality conjecture. So the main object of the local regime of the random matrix series is a correlation function, and universality conjecture that was formulated in the 70s tells that local behavior does not depend on the matrix distribution, element distribution, and depends only on the symmetry type of the matrix. So for example, if you have Hermitian matrices with any kind of distribution and you are in the localized regime, then if you consider correlation function Rk in some point inside the spectrum in 1 over n neighborhood of that point in the bulk of the spectrum, then after some normalization, you know that the limit of this correlation function should be the same as for Gaussian unitary ensemble, so it's determinant of the this famous sign kernel. If you consider real symmetric matrices, you will also have universal behavior, but the limit will be another because we have another limit for the Gaussian orthogonal ensemble. For symplectic ensemble, we will have the third limit. So I'm going mainly to speak about the Gaussian unitary ensemble, and so unitary case, so we are really interested in this type of behavior. So if we speak about this dichotomy of localization, delocalization, then for almost all classic of random matrix ensembles, we have delocalization. So that is a Wigner ensemble, that is a beta ensembles with beta equal 1, 2, which corresponds to classical random matrix ensembles, sample covariant matrices, or whatever. For all these cases, we have delocalization. From the other side, we have another classical model, which is the famous Anderson or random Schrodinger operator, which looks like that. So you have deterministic Laplacian plus diagonal random potential. So in 1D case, which is a simple one, we have matrix which has these forms here. V is independent Gaussian elements, and this one corresponds to this deterministic Laplacian that we have. It is well known that in 1D case, we have localization and Poisson local spectral statistics. That is results going back to 80s by Fröhlich Spencer and by Eisman Molchanov and other people. So the interest to random band method is simulated because it's somehow the intermediate model between these two. So random band matrices can be defined in any dimension, but we are going to speak mainly about d equal 1, so let me define it there. So we consider the random matrix. It is Hermitian random matrix. It still has independent elements, and with mean 0 certainly, but now the variance is not like in classical Wigner matrices where it's everywhere it's constant. Now the variance is given by some function j that is called the band profile. Typically this j has a compact support or a rapid decay. Again, typically it's polynomial or exponential decay. And so the variance is depends only on the distance between j and k. and it looks like that. So the main parameter of the model is the bandwidth W, which can be from 1 to n. So let me again show you the picture for 1D case. So in 1D case, the classical random band matrix looks like that. So you have a band, that is why it's a random band matrix, of the width 2W, and you have zeros everywhere else. And the elements in this band are independent elements with a typically identical distribution. So that for the compact support J, if J has a rapid decay, that means that you don't have exactly 0, but you have variance that goes to 0 very fast. Okay, and then variant W, you can somehow see that if W equal to n, you have a classical Wigner matrices. If W is somehow constant or even 1, you have just diagonal matrix, so it's somehow similar to random Schrodinger. So certainly not the same as random Schrodinger because you don't have deterministic Laplacian here. So in this talk, we consider two specific models of random band matrices. First one is this band matrices with a specific J. So we take J of this form. It is, in 1D case, it's easy to compute what is this, and you will get that indeed this J variance has exponential decay. So if distance between I and J bigger than W, you have that variance of your matrix element exponentially decay. And another second model is a little bit of the different, constructed with a different scheme. So we now consider the block band matrices. Each A, B is a block W times W. Yes, and the diagonal blocks, A1, A2, and so on, are just GUE matrix, and B1, B2, and so on are just Geneva matrices, so they have all independent elements. And we have just three block diagonals that are non-zero. All other stuff are 0. So you can see that it's, so the variance in AJ is 1 minus 2 alpha divided by W, where alpha is some constant. And the variance in BJ is alpha over W. So it's not like constant, but anyway, it's of order 1 over W. So you can see that that actually also kind of band matrices because all non-zero elements are of the band of which 2W plus 1. So such models, again, classical and was considered by Wigner. So the main feature of that is they has what is called local gauge invariance, so that you can rotate it by the product of unitary W times W matrix. So that is a second form of that. So it is well known that for any kind of band matrices, if only W and N both go to infinity, then the density of states or empirical, so the limit of the counting, eigenvalue counting measure is a semicircle law. So if only W goes to infinity together with N, we have a semicircle. So that is about global regime. More interesting question is what's happened actually with the local spectral statistic. And there is a conjecture that was formulated in late 80s, early 90s, that tells you that in D equal 1, we expected that the localized length is of order W, which from the random matrix point of view means that we expect that if W grows faster than square root of n, we expect that we have delocalization of all eigenvectors and GUE spectral statistics. If W grows slower than square root of n, we expect localization and Poisson statistics. So square root of n somehow the threshold where we expect to have a crossover from the local statistics. So there are also some such conjecture for D equal 2, D equal 3, and the main probably interesting thing in this conjecture is that they are very similar to conjecture for the random Schrodinger operator. That is why that model is very interesting. But anyway, mathematically, we not completely solve it even in 1D case. So, and we are very far from even part result in 2D and 3D. So I'm going to talk only in D equal 1. So at this point, the results that we have are the following. So from the localization side, there was a proof of Schenker in 2009 that using the technique that comes from Schrodinger operator proves that we have localization length small is w to the 8, which means that if w is smaller than n to the 1/8 power, we have localization. And recently it was improved to w to the 7. From the delocalization part, we have, first of all, the classical result of Erdős and other people tells you that with the random, since we know universality now for Wigner matrices, it tells you that L is bigger than W. That's first. That technique was used to obtain some partial results, so it's not complete delocalization because that is more weak form of each, but it was proved that localization length first is bigger than W to 7/6, then that W bigger than 5/4, but that even in a weaker sense. And so once again, we expect that L is of order W to the square. Yes, so that is what we really want to prove. So that is results that we have. And very recently, it was proved that by another technique which is new and called the quantum unique ergodicity, that W is actually bigger than n to the 4/3. Sorry, it's not 3/4, it's 4/3. But anyway, it's still far from W to the square that we expect to have. There is another approach that allows, so that is somehow the approach that comes from working with random Schrodinger and classical random matrix ensembles such as Wigner matrices. There is another approach which is based on so-called supersymmetry and Grassmann integration. That is approach that's based on representation of the determinant as an integral over the Grassmann variables. That really allows you to obtain the integral representation for the main spectral characteristics, such as the density of states, correlation function, average green function, so whatever you want, you can obtain using that integral representation using that technique. So let me emphasize that actually to obtain integral representation, it's not so hard. It's rigorous computation, and typically that is just few pages of computation with some algebraic tricks. But the real mathematical challenge and what you can do with this integral representation after you obtain it. And that is much more complicated because typically for the standard spectral characteristic, you obtain something some integral which contains both complex variable or real variables and Grassmann variables. And to analyze it, you need to understand, to analyze it rigorously, you really need some new technique that allows you to do this. So to give you an idea how this integral representation can look like, let me first say that we need to consider so-called generalized correlation function, which is expectation of the ratio of the determinant. We consider such kind of ratios. Again, Z is some point in the 1 over neighborhood or the point inside the spectrum. And why we really need, why this ratio of determinant can help us, because, for example, if you differentiate the first one and then put Z1 equal to Z1 prime, you will get the expectation of trace of the resolvents, which gives you the density of states. So similarly, there is a connection between this ratio and the second correlation function. It's given here. So that kind of ratio really allows you to obtain some spectral characteristic. Another very interesting observable that you can consider, and that is expectation of correlation polynomial. So at first glance, that is not a local object because the determinant contains all eigenvalues, not just a few one in the middle. But it's interesting thing that somehow it is expected that correlation function of characteristic polynomial has the same transition as the usual one. So it's also expected that now we know that as a theorem, that it has a transition at n of orders of w's order square root of n. And this correlation function was studied for many other ensembles, and it has independent interest in many other fields. But for example, it is known that the behavior of this function for Wigner ensemble, so for any distribution with the all finite moment, is actually, after proper normalization, are the same as for Gaussians. So will be the same, and depends only on the fourth moment of element distribution. So it's also somehow universal. Okay, so that somehow, from the supersymmetric point of view, that is a simple spectral characteristic that you can consider. And so let me show you how integral representation for that spectral characteristic looks like. So once again, we consider that is average of product of two characteristic polynomial, and then integral representation will be the following. So this J, once again, that is a band profile, so G inverse is just inverse of that matrix, and that is the integral representation that we obtain here. Xj are just 2 by 2 Hermitian matrices, so we don't have any Grassmann variables in this integration. That is the usual complex integral, nothing very strange. So if you're interested in density of states or the second correlation function, the representation will be very similar, except you have these matrices. Xj will not be 2 by 2 Hermitian matrices. For the density of states, it will be just 2 by 2 matrices, but now these two variables are real, and ρj and τj are Grassmann variables, so that means anti-commuting variables. And for the case of second correlation function, you will get 4 by 4 matrix. And here, Aj and Bj are complex matrices. Aj is Hermitian, Bj is with hyperbolic symmetry. And this ρj bar and τj bar will be just 2 by 2 matrices of independent Grassmann variables. So you will need to work with this. But anyway, that formula is OK for any J. And so it's not hard, really hard to obtain it. And generally, it looks not as bad. So now I probably have to say why I need to consider specific J, because you can see that here I have J inverse. And so if I consider J of the form this minus W Laplacian of W squared plus 1 inverse, that gives me that J inverse is a 3-diagonal matrix. So that gives me the integral representation that looks like that. And the main feature of that representation that I have what is called the nearest neighbor interaction. So I have a product only, so if I just open this parcel and obtain the trace, I will get just trace of xj minus 1. So I don't have interaction between any other j and j minus 2, for example. Yes, so that is a nearest neighbor model that allows me to apply some classical statistical mechanics technique like as transfer matrices, for example, here. And anyway, that is much simpler to analyze. That is not nearest neighbor model here. But in principle, so once again, that integral representation is true for any j and any dimension. So you can, the problem is that it's hard to analyze it for other j. But in principle, it's not like it's impossible. It's possible to analyze it for other j, probably not with a transfer matrix approach, but anyway, it is possible to consider some other stuff. So that is how it looks like. So now let me say a few words about transfer matrix approach. So the idea of transfer matrix approach is very simple. You just look at integral representation and see that it can be represented in the following form. So you have some function, and then you apply the operator on some L2 spaces. Here, for example, it's L2 spaces on a set of 2 by 2 Hermitian matrices. Yes, and you see that you have actually the power of this operator applied to two vectors, which is two functions. So you can really, then you can write this as such a sum, where lambda j of k is the eigenvalues of this operator. And so you're really interested in the spectral characteristic of this k, which is actually called the transfer operator. So, from this integral representation, you can really see that if you know the spectral property of this operator, and for example, you know the spectral gap between eigenvalues, you can actually analyze that sum and what you can obtain here. So again, for characteristic polynomials, which is a simple case, this operator k looks like that. So that is a classical difference operator that you have, and capital F psi is a function that depends on psi, so it has this kind of thing which does not depend on psi times this somehow 1 over n perturbation. So let me emphasize that the perturbation here is very small. It's complex because we have I here, but it's very small. It's 1 over volume somehow. So actually the main problem here is to study that operator. So first of all, you need to study what is the saddle point of this function f, so what is the maximum and minimum here. And the saddle points has the following form. You have 3 types of saddle point. So the first type is actually not saddle point, it's a saddle manifold. And it looks like that. So you have pi rho, where rho is semicircle law, and you have this uj is 2 by 2 unitary matrix. And this L is just 1 minus 1. So that is a manifold that somehow the sphere, because you have uj star L uj, which is a point on a sphere. Yes, and another 2 points is just really points, because you have just pi rho times identity matrix 2 by 2. Again, that is for characteristic polynomials. So what is the main problem with analysis of such kind of operator? So, and similar operators that appear for the density of states and for second correlation function. So the first problem that you can see directly here is that operator, so that function f, it's really not self-adjoint. It's the saddle point that you get here gives you the quadratic part of this function f is essentially complex, so there is no choice that you can obtain something which self-adjoins. So if you want to apply the perturbation technique, you have to be accurate, because for not self-adjoint operators, that's always a trouble. Second thing, it's quite complicated because you not only have this so it depends on this unitary group uj, so you have some kind of continuous symmetry here. And the third thing, that is the main point, that actually it's not really appear in second correlation function, but if you consider density of states or second correlation function, that is certainly the main point of interest, then your kernel, so the transfer operator, has very complicated structure. So for example, so if your matrix has 2 Grassmann, that will be just 4 by 4 matrix whose elements are operator on some L2 space, which depends on 2 by some, for example, so that is L2 space on some unitary group or hyperbolic group or something like that. So yes, and they depends on n and w. So if you're interested in second correlation function, you have 8 Grassmann, and the number, so the matrix that your transfer operators that you're going to consider will be 256 times 256 matrix, whose elements are operator in some L2 space, which depends on w. So even if you use some kind of symmetry, which is possible in this case, you will get still 70 by 70 matrix, which is still huge. The good thing here is that somehow you can see some structure on that matrix, but even to determine that structure, you need to work hard. That is why that was a big project that now almost come to its end, because now we are close to doing this 70 by 70 matrix, but we start step by step. So at first step, we consider this characteristic polynomial. Then we consider the density of states that is 4 by 4 matrix. Then I'm going to talk about sigma mode of approximation that has a 4 Grassmanns. That means that you have 16 times 16. And finally, after you consider the sigma model, you can try to consider this one. So, but let me start with the result for characteristic polynomials, because that is most transparent result that I can show. First of all, at this moment, that is the only spectral statistic for band matrices where we can really prove the threshold square root of n. Yeah, so let me consider this average of two characteristic polynomial and normalize it in the following way. Then you can see that if W is bigger than n to the 1/2 plus theta, you will have sine kernel. If it's smaller, logarithmically smaller than square root of n, we have 1. And now we even know what we have in between this. So we know what we have if W is of order square root of n, so near the threshold. And what we have is the following expression. So let me probably express what we have here. So this Laplacian is Laplacian on a sphere. And this scalar product is also on this two-dimensional sphere. And this scalar product is also scalar product in the two-dimensional sphere. Yes, so this nu is a function. So somehow I parameterize the sphere by the unitary group 2 by 2. And this nu of 2 by 2 unitary matrix is just this expression where x is off-diagonal M element of the unitary group. So you can see that if this C star is very big, then we can neglect this term, and what we have will be 1. So we have this Poisson statistics. If this C star is very small, then we can cancel that term, and we have exponent of this guy. And if you compute the integral on the sphere, it exactly gives you the sine kernel. So somehow it's easy to see that that really glued together these two results. That is what we have. So probably what I also have to say is that all these results are for Gaussian elements. So we consider only the Gaussian distribution. Generally, that is not a problem because, so it's first of all, for characteristic polynomial, you can consider other distributions that will be just more complicated, but in principle you can. And secondary, even for second correlation functions, there are techniques that is called the comparison method due to Erdős-Jau and their collaborators that allows you to compare some matrix with a more general element distribution with a Gaussian if only the first 4 moments match. So in principle, you can extend, so with some effort, certainly, you can extend a result for Gaussian case to the case with for the distribution with 4 Gaussian moments. We have no idea what to do with a distribution that does not have 4 Gaussian moments at this point. Okay, so the first result was obtained without transfer matrix approach. The last 2 was obtained with the transfer matrix approach. And in principle, the first one is also possible to obtain with transfer matrix approach. We just, at that point, just use another technique. That was how it was. But anyway, in this spectral statistic, we really know almost everything that we can. So for the density of states, situation is even more interesting because it was studied even in 3D and 2D by the supersymmetric technique, certainly without transfer matrices, but it was studied by Dissertori, Pinson, and Spicer in 2002 for 3D. So it was proved that if you consider the average of the trace of resolvent, and the same thing for semicircle law, then the difference between these two is smaller than C over W square for any imaginary part of Z. So the people who know about the local semicircle law probably understand that it's very important to have this kind of law for Z, which is, has a small imaginary part, smaller, of order 1 over W. So in this case, it's not so important because we anyway have the average. So to obtain the local semicircle law, you really need here the empirical density minus semicircle density without the average, but with overwhelming probability or something like that. Here we have average, but for any imaginary part of that. So it's not important what we have here. And in 2016, it was obtained by the same technique, which involved cluster expansion in 3D, in 2D, and with the transfer matrix approach in 1D. another important result that we have already is somehow one more step in this project, because once again the density of states has 2 Grassmann variables. Now the model that I'm going to consider now has 4 Grassmann variables, and that is called the sigma model approximation of the band matrices. So for people who doesn't know much about what that sigma model actually is, I can try to explain this on characteristic polynomial. So you have such kind of expression. So where is that? Here, yeah. So with xj. So what is sigma model, for example, for that kind of case? This xj is 2 by 2 Hermitian matrix. I want to do the following thing. I want to do the change of variables by unitary. So I want to represent xj as, let me write it somewhere here. So I want to write xj to be some uj star aj hat uj, and this aj hat will be just diagonal matrix. Yeah, so that is a change of variables. So now your variables you will have 2 real variables and unitary group that goes here. Then somehow going to the sigma model approximation means that you integrate out this aj and bj. So you put them equal to their saddle point value, and in this case, that means that you actually change your xj to this kind of thing. So you go directly to the saddle manifold, and now your integral will be only on the unitary group. So in this case, in the case of characteristic polynomial, actually the sigma model is also famous model, because sigma model approximation with these band matrices gives you Heisenberg model with a classical Heisenberg spin on the sphere. And certainly in 1D case, that Heisenberg model is very easy to solve, but in 2D and 3D, even the sigma model approximation, which gives you Heisenberg in 2D and 3D with a complex external field, is not solved yet. So that is why in 2D and 3D, it's not so clear what we can do with this technique. So somehow we do the similar thing here. So in second correlation function, your spin somehow, or your variables that you integrated, is now not, as I told you, that is not just 2 by 2 matrices. That will be what is called the super matrices. So it looks like that. But again, you can somehow diagonalize it, and with some technique, and then you will again integrate out the eigenvalues and go to this. Now that will be super manifold, and what is left will be the sigma model approximation. That is somehow what you get. But mathematically, it's not so rigorous to diagonalize it properly, because there are some problems there. I'm not really going to go deep here, but generally the sigma model approximation for band matrices is well known. It was obtained by Fetov, but again, there is no rigorous derivation of it. So the result that we obtain has 2 parts. The first part is the rigorous derivation of that sigma model approximation for band matrices, and the second part is analysis of this sigma model for somehow all the localized regimes, so for W bigger than square root of n somehow. So how this sigma model looks like? It looks probably terrible for the people who never saw it, but it's not as bad actually, because what you have here, so that is so you have such kind of integral representation, which looks like a kind of standard statistical mechanics model. So you have inverse temperature beta here, you have nearest neighbor interaction, you have some external field here, yes. So, and this Qj now is a matrix that looks like that. So Uj is 2 by 2 unitary group, Sj is hyperbolic 1-1 group, and this rho j hat and tau j hat is just diagonal Grassmann matrices. So each of them is diagonal, has two independent Grassmann on the diagonal. And that's how it looks like. Again, that's probably not necessary to understand that. And the important thing that it has this qj square equal to 1, which is similar to what Yefetov has in his model. So somehow that model is very similar to Yefetov 1 that we have. And the regime that we are interested here, so the crossover for this case is expected when beta is of order the volume. So beta is of order W. So delocalized regime should be if beta is bigger than n, and localized regime is expected to have if beta is smaller than n. Okay, so actually, why the sigma model is so important? Because typically that continuous symmetry, so here it's uj, here that will be more complicated superunitary groups that we have. It's believed, people believe that it has all qualitative physics properties. So somehow that all these problems, so all these kind of thing that's responsible for the crossover is actually lies here in this continuous symmetry, not in the integral or the eigenvalue. But certainly mathematically, if you're interested in the whole model, you first need to explain why you actually can integrate out these eigenvalues. So again, let me formulate the theorems that we get. So in dimensional d equal 1, we obtain that indeed the behavior of sigma model approximation if beta is bigger than n in the bulk of the spectrum coincide with those for GUE case. So we really have the determinant of the sign kernel. So we prove that, first of all, for energy which is smaller than square root of 2, but that is just technical assumption. We are sure that it's true for any point inside of the spectrum. And secondary, so mathematically, somehow that means the following. You consider J of this form. So you divide by here, not by the initial form that I consider was here I divided by W, not by W squared. To obtain the sigma model approximation, you first need to divide by W, so rescale your beta here. Then you have to put W to infinity. And after that, beta and n should together go to n. That is how somehow the sigma model limit that you have. So first, W goes to infinity, and then beta and n together goes to infinity if only beta is larger than n times log square. So the right limit, so the actual limit that you need to study the correlation function is the following. You take beta of order W, fix this alpha, and then Wn and n both goes to infinity. So that is somehow the right limit that you're going to consider, which is certainly much more complicated. But that is work in progress right now. So now we have some hopes that we can manage to work with this 70 by 70 matrix, because somehow it's big, but it's kind of tensor product of matrices that we obtain here in sigma model approximation. And that, in principle, what we expect to have, because once again, it's believed that sigma model is the most important part of the model, because that really has all property, all important physical property of the model. So I still have some time, so let me explain a little bit how we apply this resolvent version of transfer operator. So since the transfer operator is rather involved, even for characteristic polynomial, as I told you, it's not self-adjoint, it has some continuous symmetry, so it's not simple, even for that case. We apply what is called the resolvent version of transfer operator, so we write that kind of integral as complex contour integral of the resolvent. Here, the contour that we have should be any contour that contains all eigenvalues of the transfer operator. So in our case, it's easy to prove that the norm of k is smaller than 1 plus c over n. So we know that it's can be bounded by some contour L0, where lambda star is the top eigenvalues of operator k that we have here. So generally, we can choose any contour L, which has all eigenvalues, because that is actually the point of some residue of this resolvent, yes. So, but it's more useful to choose contour as follows. So we choose this L2 contour, which is somehow has all eigenvalues starting from some point, and another contour has eigenvalues with numbers. So that's eigenvalues will be lambda 0, lambda 1, and so on, and lambda 0 is the top one, lambda 1 is the next one, and so on. Then somehow we encircle all eigenvalues starting from number log n in one contour, and the first contour just encircles the first log n eigenvalues that we have. Then it is easy to check that the second contour is not really this contour is not really gives any contribution, because you have z to the n here. So if you consider z to the n, you will get something like that, and that is exponentially small in n, so you're not really interested in this. So the most important part is this contour L1 that encircle first log n eigenvalues somehow. So the first step in the analysis is that somehow you have to prove that only the neighborhood of your saddle, as always in saddle point analysis, you have to prove that only the neighborhood of the saddle points gives you some contribution. So first of all, you need to go to the neighborhood of your saddle point and prove that actually, as I told you, where it was, yeah, here. So we have three types of saddle points. So first of all, you need to prove that only the neighborhood of that saddle points gives contribution. Secondary, you have to say that saddle points are really not important. They give less contribution than the main contribution which comes from this saddle manifold. So that is what you did. After that, you actually say that you have two, we say that operators are asymptotically equivalent if this expression that you have are of the same order. So they can be multiplied like that. And the main idea is that you don't know how to analyze the operators that you have, but you can find the operator which is asymptotically equivalent to your operators that you can analyze actually. And so somehow the next step is to prove that the operators that you have. So again, probably what I have to say, let me show you. Yes, it's here. So as you can see, this operator depends on x and y. So x here depends both on eigenvalues and unitary group here. So and that is true for f, for f and xi. So anyway, that function depends on both variables, eigenvalues and unitary variables. So the idea is to prove that your operator that depends on all variables can be actually written that it's asymptotically equivalent to the product of tensor product of two operators. Each of them depends only on one variable. So first one depends only on unitary group, the second one depends only on eigenvalues. That's somehow the same thing as to go into sigma model approximation somehow. I not really want to do it rigorously, say something about that rigorously, but that is actually the main step and the main technical step that you need to work with. And that operator on unitary group that you will have, it looks like that. So it's some operator that depends only on the difference between two unitaries. And it has perturbation of order 1 over n, which looks like that. And that nu is once again 1 minus 2 elements of unitary group. So somehow, if you put all u equal to each other, then that will be this k star 0 will be 1, and what you get after, if you consider the power, will be just e to the minus ix in u, which, if you integrate, gives you the sine kernel. So then, if you can prove this, you can actually analyze not that operator, but this operator, which is a tensor product. And this allows you actually to come to analysis only of that operator. So you somehow forget about eigenvalues because they will be cancelled, and you analyze only the operator which depends on the unitary group. That operator is still not self-adjoint because you have this aix here, but operators that you have inside, so without perturbation, this operator is self-adjoint. And moreover, it's a good operator that you can analyze without any difficulties because you know that is a difference operator in U1, U2, so you know that its eigenvalues and eigenvectors. So it is known that eigenvectors of such operators is Legendre polynomials, and you can compute the corresponding eigenvalues that will be like that. So that T star is some constant that depends on density. I'm not really want to write it directly, but that is constant that depend on density. So you can see that at j equals 0, you will get 1, then you will get 1 minus 1 over w square, and so on. So the first gap between these eigenvalues is 1 over w square. That really gives you that the transition should be when n is of order w square, because that is a typical thing. So, you don't know that operator is self-adjoint, but you know that that operator is a small perturbation of operator that is self-adjoint. So you can write this operator that you are interested in that depends on xi as this operator that does not depend on xi plus some perturbation of order 1 over n, like that. And so you know that the eigenvalues of this operator is in 1 over a neighborhood of eigenvalues of that operator somehow. That's how it goes. So from this case, it's really clear how you can study the spectral characteristic of this guy. So if we on the regime where w to the minus half is much bigger than 1 over n, that means that the spectral gap between two first eigenvalues is much less than the perturbation. Then it's easy to check that, so we can compute the first eigenvalue and prove that all other eigenvalues are actually very small. They really much smaller than this power. So once again, we're interested in the nth power of each eigenvalue. So if we have something like that, then the n power just goes to 0. That is why we are not interested in that. So that gives that actually somehow the nth power of your operator gives you the projection only on the first eigenvalue and first eigenvalue that we have. So in this regime, we will get that only the first eigenvalue is important. So the top eigenvalue is important, and so the value that we compute is actually can be computed like that, which is also can be proved that it goes to 1. And such a way we obtain a Poisson spectral statistic. If we are in another regime from the other side, then the nth power of this difference operator goes to 1, and so you can write that the nth power gives you this scalar product. And because you have just this 1 over n perturbation. And that scalar product is exactly the sign kernel. You can compute it directly, and you will see that that is a sign kernel. So in the middle of that guy, you need to compare the eigenvalues that you have with the eigenvalues of the Laplacian, which also very simple to compute. The Laplacian and spherical Laplacian is well known, so you can compute the eigenvalues of them. And you will see that actually the 1 over order n perturbation now looks like that. And so the n power gives you this Laplacian that we have. So the last thing that I want to show you that there are some results with SUSY technique that obtained for the second correlation function, but without transfer matrix approach. The first result was obtained by the full matrix, so it's not like sigma modular approximation, and that is for the full matrix, but with a number of block which is of order constant number of blocks, which means that W actually is of order n. So it can be n over 2, n over 3, so on, but it's still of order n. And that gives you that we really have, in any dimension, in this case, we will get the sine 1 minus sine square. And the second result was obtained by Erdős and Bau. It was for the similar model, which is a little bit more complicated. It was obtained by green function comparison strategy that the same result works for first of all for n bigger than w bigger than n to the 6/7. And secondary, it was obtained, so for Gaussian, and then with this green function comparison strategy, it was obtained that it's also valid for more general element distribution with sub-exponential tails and for Gaussian moments. So thank you for your attention.
Thank you very much. Okay, thank you very much. So questions? Comments?
I had a question about the this for Gaussian moments. Is the technique the same as the Talvu moment matching method, or it's slightly kind of different?
Yeah, it's a technique that comes from Erdős papers, yes, and they're together paper with Talvu, so that is the same technique, yes. So that is why we have 4 moments matching. So the problem, so in Wigner case, they was able to obtain the more stronger result because there is a result of Johansson that gives you Gaussian perturbation. Yes, there is no such result for this case. That is why we're not able to obtain something with for example, 2 moments Gaussian, like it was for Wigner case.
But do you expect the result to still be the same?
Yes, yes.
Okay. And one other thing is what happens just with the characteristic polynomial case if you try to add another?
I never tried to work with characteristic polynomial of band matrices with other distribution because even with Gaussian case we are not really.
No, I mean if you just include another factor, so you have product of two characteristic polynomials.
I didn't try that for band matrices, but I did that for Wigner matrices, and at that stage I was able to compute everything with this. So I expect that for band matrices, it's for second moment, so for just two characteristic polynomial, I expect that it's also possible to compute it for more general distribution.
Thank you.
So any other questions?
So have you thought about band matrices with periodic boundary conditions?
That's also possible, so there's not much big difference generally, but for our purpose it's more simple to consider it with Neumann boundary condition. But generally that should be the same thing. So it's,
even the cases where you don't get the semicircle, like when they
no. I work only with where we have both W and n goes to infinity. So I don't know what will be in other cases, but in this case, if W goes to infinity, I think that periodically boundary condition is also fine. It's not a problem.
Okay, thank you.
Sorry, but so if you leave W equal to 1, what can you say about?
Nothing.
Nothing. Okay. So three diagonal matrix, there is nothing, no results.
No. So yeah, it's even so. The problem that you even don't know exactly what will be the global regime. So you don't
that's
know
what I'm
the
asking.
density.
Not even the global regime, except for the Schrodinger operator.
No, but Schrodinger has this Laplacian. Yes, so it's a little bit different.
But
no,
if
as far as I know, there is no nice result with a finite W here.
Okay. So any other questions? Okay, so if not, we thank Tatyana.